Okay, let's start. Today I will introduce you the pitch tracking and what is pitch tracking and the in algorithm, which is a very basic algorithm of pitch tracking. So let's start. First, what is pitch tracking? If you search in Wikipedia, it tells you to catch it's to catch the fundamental frequency with time of a given audio. And the fundamental frequency is actually the lowest frequency partial in a harmonic sound. Okay, so let's first look at some examples. And fundamental frequency are often abbreviated as F0 in academic papers and books. Well, let's listen to this signal first. This is an oboe sound, and if we intercept a very little period here, it will give us a waveform like this, right? And if you conduct DFT to this intercepted waveform, then the spectrum will be like this. So F0 is this, the lowest frequency. And sometimes people will misunderstand F0 to be the highest magnitude one, but it's not. It's the one with the lowest frequency. And another thing you may observe from this spectrum is that all the higher partials are integer multiples of F0, right? They are of equal distance, and this is F0 and this is 2F0, this is 3F0, and so on. And this happened to most harmonic sound. Okay, so this is the spectrogram of the signal. And have you attended the last tutorial? Okay, so I bet you still remember how this is conducted, right? And again, this is F0, the lowest one, right? Not the highest magnitude one, because the darker the color, the higher the magnitude will be. But we didn't choose the deepest one. Okay, another example, because the oboe sound may oscillate very regular. Let's look at a human voice. Okay, that comes from me. And again, if we do, this is a small period in between. And if we do a DFT, then, well, F0 heights here, it's very low, but actually it's F0, not this one, right? So please be careful of the definition of F0. And well, the human voice contains much more partials than the oboe. The spectrogram looks like this. And if we zoom in a little bit, we'll see that this is F0. Okay, so something more about fundamental frequency. As I said, the equal distance between different partials is mostly, but not always true. For some instruments, they actually, like xylophone and even piano, the higher notes of piano, they actually does not oscillate very regularly. So sometimes the equal distance will be not that strict, but there are still harmonic voices, and they're still very good choice for. I mean that equal distance doesn't appear anytime, but mostly. Okay, the second point is the lowest frequencies could be missing. Let's give an example here. This is the original oboe sound. Right, this is the spectrum. And if I eliminate the first frequency here, let's listen to it again. There isn't so much difference, right? Even if we eliminate two frequencies, partials here, yeah, the sounds change. The sound changed a little, but you can verify that it's still the same note. It does not go to a higher note if you know music instrument, right? So the fundamental frequency does not change by eliminating the first or second frequency partials, or even more. But the more you eliminate, the less information you will keep. So, well. And the third point is that for a sound with harmonic partials to be heard as a musical tone, typically it contains at least 3 frequency partials as a harmonic sound. This is mostly this comes from people's experience. So don't ask me why it's 3, not 4, not 2, not 5. Okay, that's experience. Okay. So what a pitch tracking algorithm will do? It will generate a figure like this. When we do this, or let's listen to the audio. Okay. So the blue line is where we have very high confidence to predict that the frequency is here. Well, I changed the vertical value to music note. So this is -1 means 1 octave lower than the standard 440. Okay. And this is another example. Okay. The algorithm will produce a very intuitive way for you to understand the pitch, right? Okay. So how should we do this? And the Ying algorithm, these two figures are actually produced by the Ying algorithm. Okay, before we go into the Ying algorithm, let's look at state of art of some pitch tracking algorithms. When talking about pitch tracking, people mean both monophonic and polyphonic. Monophonic means there is only one audio source in the audio. That means if you only one people singing or only one music instrument playing, no background, right? And polyphonic is the opposite. Several people are singing together, and a band is playing. That's all polyphonic. And monophonic problems are basically considered solved today. And you can see the Ying algorithm lies here. It's not the state of art now, but it's a very good way and intuitive way to start because it does not go into the frequency domain, and it's a bit easier for people to understand. Okay. Let's look at the Ying algorithm. If you look at the Ying algorithm paper, you will find that it has 6 steps. And the first step is the autocorrelation method, which was the state of art in 1970s, I think. However, the 5 steps here are all modifications to the autocorrelation method. Okay. So first we will look at how autocorrelation method do the pitch detection, and then we will see what's the disadvantage of that method. Then we'll look at the modifications. Okay, so first let's look at the autocorrelation. If you attended my DNT tutorial last time, you have met this correlation function. It's a comparing between two signals, and we compare the similarity. And this time, we calculate the correlation between a signal and another signal which is itself shifted for tau beats. Okay, for tau beats. Well, if we happen to choose tau as the period, then this function will be the largest, will reach its maximum. Because if you compare a function with itself, the correlation will be high. And if tau is not a period, the function will not be as high as when tau is the period. Okay, that's the basic idea of this. Okay. So let's look at a signal. Okay, so I choose a timestamp t, and I shift the signal itself by tau beats. Here it becomes t plus tau, right? And if tau happens to be the period, then no matter we start from t or t plus tau, it should be the same, right? However, now I didn't choose tau as the period, so there's a slightly difference between it. Well, anyway, we choose a window size, and we compute the correlation between these two parts. And we get f tau. Because we're going to do this for tau equals from 1, 2, 3 to tau max. And tau max is, well, depends on the lowest frequency you want to detect, or the longest period you want to detect. Okay? So please understand f tau. F tau means I compare the original signal with the signal which shifted itself by tau beats. Okay, problems with f tau? Okay. Then I will plot f tau from start from 0 to tau max and see what happens. Yeah, so this is the original signal, and this is f tau. And you will see that the periods appeared exactly as well, right? They are similar. So how do we calculate the fundamental frequency from f tau? Generally, we actually want to choose. Well, we actually want to know the distance between the two peaks, right? That's the period of the original signal. Yeah, because fundamental frequency, so how to recognize fundamental frequency from the time domain? You just find the repeated pattern. So from here to here, that's the period of the fundamental frequency. Okay? Well, gonna appear like this. Well, another question is that you might ask why we just do a DFT to this and choose the lowest frequency partial. That would be easier, right? However, in real signals, there will be a lot of noise. And if we do DFT, and we don't know which frequency to choose, because in the lower parts of the DFT spectrum, there will be a lot of peaks. So yeah, we actually don't know which is the F0 we want. And if we use the time domain method, it will be a little bit clearer, but not very clear actually. The problem of autocorrelation function still lies here. And this period, for this signal, it oscillates very regular, so we can see a perfect periodicity appear at the autocorrelation function. Our job is to calculate that. Yeah, we actually want to count this, the first peak, right? The first peak of the function, and we want to this peak, and if we are given it with a sample rate fs, then we can calculate the f0 through this. Because well, just calculate this quickly. Tau 0 is the number of beings. It's a signal period represented with number of beings, right? So one being stands for 1 over fs second. Okay? And tau 0 being stands for tau 0 over fs second. And that's the signal fundamental period. So how do we get from period, transform from period to frequency? And we just use 1 over period, that's the frequency. Okay? So if we detect the first peak of the autocorrelation function, we get the fundamental frequency. Well, however, let's look at another example. This is another sound wave. It oscillates not very perfect, but yeah, we can still find the first peak to detect the fundamental frequency. Okay? This is actually the value, the peak we want to find. Okay, and this is another example. Okay, this is a piano series, and we just choose the small period here. And you can see it's near the end of one note, so it's not very perfect oscillate. And if you I can judge from my ear that it's a G5 note. It's approximately 784 Hertz. However, how does computer do this? If you calculate the DFT spectrum, it would be like this. However, this time we want to find this peak. And these are noises. So this time we don't know. If you remember in the oboe sound, the noise is very low compared with the peak. However, this is very high, so we can't use any frequencies here. And again, the autocorrelation function does not seem good because, well, for this function is good because we want to choose the we should choose the first peak actually here also, sorry. The green line should be here. Okay. We need to choose the first peak here. But it's not as high as these ones. That will bring you some problems. If you remember if you remember this figure, here also appears a maximum. And why we want to choose this maximum other than this? Because it's higher, it's much higher. And this maximum only stands for some frequency partials. And this stands for the fundamental frequency. However, okay, so it will bring you a problem that how do we choose which peak we want, right? And okay, you cannot say that I will choose the first peak, second peak, third peak. That's not always true. So you cannot hard code this. And okay, so you said I want to choose the highest peak. For example, you want to choose the highest peak. Then here you will fail, right? You want to choose actually this is the correct peak. However, if you choose the highest peak, you might choose this one, or even this one. That's far not right because of noise. People actually created some. Well, yeah. First, let me introduce two kinds of arrows: the two high arrows and two low arrows. Two high arrows means you detect a lower period to get a higher frequency. And two low arrow is the opposite. You detect a higher period to get a lower frequency. And for example, if we choose this peak other than this peak, it will be a too low arrow, right? And in this figure, too low arrow will be more likely to happen than too high arrow, because there are no peaks, no maximum before this peak, right? So no high arrow may not happen, right? But too low arrow is very likely to happen. However, in this figure, the too high arrow is very likely to happen if this peak is very close to this peak, right? For example, if the figure is like this, the peak reaches here, then, right, you should choose this one other than this one, but you don't know what to choose. So in this figure, the too high arrow is more likely to appear. So, one method that people invented to combine with autocorrelation function is that they add a damping coefficient to the autocorrelation function. To the autocorrelation function. After damping, when tau increases, the function will be close to 0. It's a damping coefficient. When tau increases, the coefficient decrease, and the function value will be smaller and smaller. I just multiplied a coefficient to this function, and become this, right? Okay, so then the first peak is higher than the second peak now, because the second peak suffers from more damping, right? Before it's like this, and after it's like this. So now we can have more confidence to choose the first peak, because because we add the damping, right?
Sorry, the lower axis is tau, is it?
Tau. Okay. Okay, but the damping autocorrelation function actually increases the other arrow. Okay, because you lowered the magnitude when tau is big. So if we meet this one, if you lower this and increase this, you'll be more likely to choose this, right? So if you add damp to this function, the accuracy will be lower. However, if you add damp to this function, the accuracy will be higher. So that's also a problem of damping. Okay, so that's the problem of autocorrelation function. If you want to use autocorrelation function to detect the fundamental frequency, you always meet with these problems. So basically, people will choose a frequency range. You know, if you for example, I want to choose frequency from 100 hertz to 200 hertz, then you will only detect the maximum within some band, right? So that will increase the accuracy very much, because you only want to detect a peak in some band. If the band only contains one frequency, one peak, okay, that would be good. But mostly people do not give a predefined frequency range. So let's move to step 2. Step 2 actually doesn't change much. It just changed the autocorrelation function to a different function. Okay, so what is difference function? For signal with very perfect periodical function, this should hold, right? And we change this formula to this. That means we intercept a signal length of W, an atom. I shift the signal by T. They should be the same, right? Okay. So the problem becomes, I want to find a tau that minimize this function. Okay, it should be very similar to autocorrelation. Other than that, I want to find a minimum other than a maximum. Okay, let's look at what is like. This is the original wave. This is the autocorrelation function, and this is the difference function. So the minimum appears exactly the same position as the maximum. So it seems it doesn't make any difference. Well, but the benefit of this function is that it gives us a solid value, or to say that this is a perfect period and that's not a perfect period, because we have a concrete value to compare with. It's 0. If the function reaches zeros here, then that means it's a perfect periodic signal. And maybe this is not 0, it's 0.1. Okay, so it's good, but not that perfect. Okay. But here we don't have that line. The signal could be any height. Okay. So that's a difference function. Well, however, difference functions still have the same problem we just met, because minimum appears here. Again, we could choose this minimum, right? Especially the function starts from 0. So that means the computer will think the points near 0 are a very good periodical part. If some noise caused a minimum appear here, the computers could choose this. So that makes us move to the third step. The benefit of the difference function is that we get a fixed optimal value to compare with. Okay, next step is that this is it's the same that we want to choose this minimum, but well, it's just the opposite of the former autocorrelation function. Okay, the step 3 is that we substitute the difference function with another function called the cumulative mean normalized difference function. And what it does is that it divided the original difference function by the mean of the former calculated values. If you want to calculate D10, you use the D10 to divide the mean of D0 to D10. Okay. So the benefit of this value is that this function is that it only gets below 1 when d tau gets below the cumulative mean. Let's look at it. It's like this. So it starts from 1, because if you only have one bits here, d1 will always be 1, right? So it starts from 1, and it will only get below 0, below 1 here. So even if there's some noise appeared, we won't choose that. We'll only look at these minimums. Problems? This is the original difference function. Okay. So this function avoids a too high error because we won't choose the functions here anymore, even if there's a noise close to the minimum here. Okay. And there's another problem. So step 4 actually tells us how to choose the minimums here, because we still found that we're more likely to choose this, right? So step 4 just tells us, okay, I set absolute value threshold, and I will only look at the minimum below this threshold, and I choose the lowest minimum below that threshold. That means if I choose a threshold here, then I will only look at the minimum below this threshold, and I choose the first minimum here. Okay. So this step kind of eliminate the too low arrow. I mean, it lets you to choose the smaller period, because you're always choosing the first minimum. However, it depends very much on which threshold you want to choose. And if you choose a threshold here, well, it will return this value. That would be very bad. So it's not the lower the threshold, the more accurate it is. So it still depends very much on the signal noise. Any questions here? Okay. So in the previous 4 steps, we'll only look at the minimum within integer value. I mean, when you calculate the f0, you use a tau 0, right? And tau 0 will always be an integer. However, the minimum does not always appear at integer value because your frequency can be any value. So the period can be any value. So we'll do a parabolic interpolation to find the optimal value here. Okay, this is very easy to understand, right? Okay, this is a formula. Just if you know that, it will be very easy to implement. So don't worry. Okay, so then we reach the 6th step, which is the last one. Okay, after the previous several steps, we actually can decrease the error rate very significantly. But there's another kind of, well, okay, but since we don't know what each signal will be like, so, I mean, after these steps, when people implement the algorithm on their projects, and they find that there's one type of error that occurs very frequently. That's they call it the octave error. That means you mistakenly choose this value over this, because this is 2 times this. So the frequency you calculated through the wrong period will be an octave away from the real period. So people call this octave error. And for decreasing the octave error, people use this method. Okay, let's look at 3 successive frames in the audio. In frame 1, we detect T1. I mean the fundamental period, okay? And T2 and T3. And since the length of 3 frames are shorter than the maximum period we want to detect, so we suppose that there won't be octave jump in the audio within these 3 frames. And if you remember that for T1, T2, T3, we both have difference function value, or the cumulative normalized difference function value. And that could be treated as the confidence, okay? The closer it to 0, the higher the confidence. So we choose the highest confidence among T1, T2, and T3. For example, if T3 occurs, the confidence of T3 is the highest, then we assign T3 to each frames. Because, you know, the target of this step is to ensure that T1, T2, T3 does not have octave jump. So, before we conduct this step, T3 and T2 might be 1 octave away. However, we're going to choose the frequency of the highest confidence and assign it to each frames. So why we choose 3 frames here? It can be a lot of frames actually. It can be 100 frames, as long as the frame size and the whole length of this signal is lower than the fundamental. It's lower than the longest period you want to detect. For example, if you want to detect the frequency as high as 4 Hz, then maybe the periods corresponding to 4 Hz will be very long, right? Because typically it's 100 Hz, 200 Hz, and if the period is very long, I will assume that in this period there will be no octave jump. So, and this length of period will contain a lot of frames actually. Well, this algorithm actually, okay, now we actually come to the end of the Ying algorithm, but I would say that this algorithm is more like an heuristic way, or based on experience. When people choose functions, they cannot tell too much scientific meaning of that function, or something that they just found that this step can increase the accuracy. So when I understand this algorithm, I would say that do not focus too much on the details about why we choose this function, what's the mathematical background behind that. All of these are engineering oriented. So, and every step is based on is aimed at increasing the accuracy. So don't struggle too much with the details. Okay, let's come into some interesting parts. Okay, we have seen this. The yellow plot here is of very low confidence, and the blue plot here is very high confidence, which means maybe in this frame your difference function is 0.01, and here it might be 0.3. Okay. Again, this is so actually the benefit of the Ying algorithm is that you can actually plot the pitch according to the confidence. So in some algorithms they just derive all this. First they detect which frames contains voice by other metrics like sound energy or some other things. But the Ying algorithm don't judge this. Just they can plot it. So during this part, in the audio actually the signal is breathing, right? So it's not a very regular periodical signal, then the difference function is high, then comes like this. Okay, let's look at some irregular things. Okay, so for very complex sound, this doesn't make any sense because the in algorithm only aims for the monophonic sound. Okay, and this one is okay. Actually, this is very good here. However, this is the octave arrow jumps, right? So and this is very high jump. So that's what we want to avoid. And some other strange things. Okay, so again, it does not make any sense, but you can see the contours there. And some other. This is a Mandarin Chinese speech.
我觉得我的普通话非常标准。
Okay, so well, if you know Chinese, right? It actually catches very good contour of different tones. However, it's not very okay. If you know Chinese, you'll see it's good. But if you're learning Chinese, it's not accurate enough. So actually, I've made another project that asks you to implement the pitch contour of Mandarin Chinese speaking to help foreign learners or people who does not know tones to learn the tones through pitch tracking. So that's a very practical use of this algorithm. Okay, last I want to talk about some metrics of evaluating the pitch detection algorithm. The first error is that okay, so in the ground truth, this frame has voice, and I detected it as voice, but I detect a wrong pitch. So I'm calculating the proportion of that kind of frames. So, and the second one is for standard deviation. It measures how stable our algorithm will be. If the algorithm, for example, if the pitch is like very stable, and our algorithm will be maybe some octave arrows appear, so the second metrics will be low. And the third one is that the proportion of frames which we're mistaken whether the frame is voiced or unvoiced. So if you remember, the first metric is that the proportion of frames that okay, so it has voice, and I detect that it has voice, but I detect the wrong pitch. And the third one is that okay, it has voice, but I detect as a non-voice. So they are different kinds of errors. And the fourth one is a combination of the first one and the third one. That means if you want to use one metric for the whole algorithm, you'll probably prefer the fourth one. Okay, that's probably all for this. And actually, we have a group project in the algorithm. This is one choice for you. In the project, we ask you to implement the algorithm or the 6 steps. And I think in the other, you have three choices, I think. And for this project, actually, you only need to implement the algorithm. You does not need to do other things. And if you have more time and you're interested in this field, you can try to implement the Mandarin Chinese pitch tracking, because the performance of the algorithm on that is not very accurate. You may try to implement a picture the contour of the Mandarin Chinese as a bonus part. Well, you will see more about this after the project specification is distributed to you. Okay, for now it's just this. So actually, if you want to implement the algorithm, I think you need to read the papers carefully. And if you are, I think if more people choose this, I will maybe give another tutorial on the paper because you need to understand the paper to implement this. Okay, so we need to go.